Okay, so I'm going to continue the all-Australian morning session here. In fact, all Brisbane morning session, even more local. Okay, so I want to talk about a few different things. The second part of the talk is going to be about some recent results in non-convex, unconstrained smooth optimizers with complexity guarantees, a Newton CG method. But I wanted to start off with a little bit of background and some kind of random half-baked observations since, as you'll see. Okay, so first of all, this thing started appearing on my Twitter feed about a month ago, and I've seen a few versions of this. This is from SAS, which is this company in North Carolina, and it's a machine learning algorithms cheat sheet. IBM has a similar one. And the idea is it's some sort of decision graph about, I've got some sort of data problem, what sort of algorithm should I use? So it ends up, you ask a bunch of questions, yes, no answers, and you end up in one of these rectangles which tell you what sort of algorithm you need, okay? And the thing that struck me about this was that many of these were sort of needed optimization methods to solve. So the yellow ones are the ones that needed some kind of optimization. You could argue about whether these are optimization, but if you're doing sparse PCA, that's optimization, I guess. So I count that in the optimization camp. So about half of the algorithms it looked like were some kind of optimization, okay? So therefore, what do I conclude from that? Well, optimization is important in machine learning, and so the whole topic of this workshop, I think, is kind of well conceived. So it is a major source of algorithms. In what sense? Well, formulating problems from machine learning and data science as optimization problems gives you a kind of rigorous way of taking statistical principles, risk, likelihood, significance, generalizability concepts, and so on, and writing them down in concrete measures and functions that you can then attack with an algorithm. So the formulations part is important. The algorithms part is important. I'll say more about that. There are a whole lot of algorithmic tools from optimization that have been developed over the last 50 years or so that turn out to be relevant. However, usually the context is important. You can't just sort of take a black box piece of software that was written 20 or 25 years ago and blindly apply it. You have to be very careful about how you do that in order to exploit the structure and in order to respect the statistical context. Duality turns out to be important in several instances. Kernel learning is probably the one very striking example of where duality turns out to be very useful in formulating the problem in a nice way. And then non-smoothness is also important in the sense of writing down regularized problems that have better generalizability properties. And so that's driven a lot of the recent algorithmic development as well. So I would say that machine learning's influence on optimization has been quite strong in sort of reorienting some of the priorities that we traditionally have in optimization, because machine learning people have somewhat different perspective about several issues. So one is that, at least the strain of optimization that I was trained in, we didn't care too much about things like computational complexity and global convergence rates. Except when I was working on interior point methods in the 90s, then we cared about complexity. But apart from that, we were sort of happy to show that any accumulation point of the algorithm was a stationary point. That was good enough. We didn't care so much about complexity. Well, machine learning people care a lot about that. I think it's due in part to the fact that there's a strong strain of theoretical computer science involved, and obviously they care about such things. And so that's caused us to take another look at a lot of algorithms and to try to prove things about complexity. Another thing is that fast local convergence rates are less interesting to machine learning people. We cared about those a lot in optimization, that you get some sort of asymptotic superlinear rate, for example. Machine learning people are much less impressed with that. And I speculate that maybe it's because the domain of fast convergence often happens when you're below the level of accuracy required for the empirical risk. Usually you're working with some sort of empirical function, not the real function that you really want to minimize, and you don't see this fast convergence until you get close to the solution when you're in the domain that you don't really care that much. So that's a little bit of loose talk there, but this is a workshop, so I can toss out some loose talk. And the other thing is that in general, well, quite often, you prefer a cheap approximate solution to an expensive accurate solution, and that's somewhat tied to the same point. Okay, and this is kind of a laundry list of algorithms from optimization that have become interesting in the machine learning context. Most of these are very old, okay? Maybe ADMM's a little bit newer, but many of these ideas go back decades, to the 50s even. And you know, these have been dusted off, dug out of the closet, enhanced, re-examined, new things have been proved about them, new variants have been developed and so on. And these are all sort of the convex case, most of them are convex, but even in the non-convex case, which is mostly what I'll talk about, this trend continues. So steepest descent, maybe with the injection of a little bit of noise to escape saddle points. There's been a lot of analysis of that recently in the non-convex context. Trust region methods traditionally have done better at non-convex problems than line search methods. And so there's been a little bit of a renewed interest in those. Nonlinear conjugate gradient and LBFGS, these are methods that work on non-convex problems. And then I'll talk a little bit about Newton's CG. Okay, so this is my slide where I really get into the half-baked, you know, model of tossing out some ideas that, you know, because it's a workshop, I'm free to say loose things, and you can all tell me I'm completely wrong-headed about this. But I was just thinking about this yesterday while I was stuck for 4 hours in Minneapolis, that, you know, the word algorithm in machine learning, it seems to me it's often used as the to denote the process that takes a training set and maps it to a predictor, okay? So you start with a training set, you end up with a predictor, and you hope that you end up with good generalizability, that the predictor does a good job on the unseen data, okay? So I think that's how machine learning people tend to use the word algorithm. Maybe I'm wrong about that, but you can correct me if I am. So when you come to use optimization, it seems to me that you're breaking that process, or you're breaking the algorithm into sort of two steps. There's a step where you write down the optimization problem, and there's a step where you apply the optimization algorithm. So it's somehow decomposed. And so in this sense, if you're doing the machine learning algorithm using this optimization toolbox, the responsibility for getting good generalizability, which seems to be the overall goal, sort of falls on both the optimization formulation and the algorithm, okay? And it seems to me that that's putting a lot of responsibility on the algorithm that wasn't there before. You know, back in the good old days, it seems to me that those of us that worked on optimization algorithms, people gave us the formulation and said, solve this problem, find the minimum of this problem. Well, that's not necessarily true anymore in this context. Nowadays, the algorithms are kind of pursuing a more nebulous agenda. They're not, you know, necessarily solving the formulation anymore. They're not taking the formulation as given and finding a solution. They've got to have good generalizability properties, which may not be completely reflected in the formulation, okay?
So why is this nebulous? I mean,
because it's not reflected in the formulation.
Because it's anything that is not optimization is nebulous.
Well, maybe so. I'm just telling you, this is a little unfamiliar. I mean, and here are a couple of examples of new questions that arise because, you know, these are sort of unfamiliar questions which back in the day we didn't have to deal with in analyzing optimization methods. So for example, there's this issue recently, there's some speculation that doing SGD with small batches gives results with better generalizability on neural nets, okay? So this says nothing about whether it does a better job at minimizing the training error. It's just that, you know, maybe you find a solution, approximate minimum of the training error, whatever, that has better generalizability properties when applied to unseen data. And the second one is, again, there's been some recent work on this, is that if you do SGD on a neural net and start with a random solution near zero, initializing the weights near zero, you tend to go to a low norm solution, okay? And that seems to have better generalizability properties. So these are kind of, you know, requirements or properties of the algorithm that don't necessarily have all that much to do with whether or not it minimizes the objective. Well, they have something to do with it, but it's not exclusively determined by the objective. Anyway, so this is my controversial half-baked slide. Feel free to attack me now or later or tell me how wrong I am. I'll learn something because I'm sort of, you know, these are issues I've just started to think about, and I think many people here have been thinking about these things for much longer. Okay, so here I've listed a few problems in data analysis that need convex optimization technology. These are very familiar to many people. Linear least squares goes back more than 200 years. linear SVM, logistic regression, and so on, compressed sensing. So, and even low-rank matrix completion, if you write down you can solve that using convex optimization technology as well. But in recent years, there's been more interest in non-convex formulations. This is actually a very old one that I'll say a little bit about, non-convex least squares, non-convex regression, low-rank matrix optimization when you write down an explicit low-rank formulation, tensor factorization, and of course neural networks. Okay, so least squares, I just wanted to say a little bit about this because this is actually the first thing I worked on in optimization way back when I was doing my thesis. So this is where you've got, the objective is a sum of squares of a bunch of nonlinear maps. And the interesting thing about this is that if you take derivatives, first and second derivatives of this objective, the second derivative has this interesting structure where it sort of decomposes into two sums. And the first part of it just depends on the first derivatives of the individual residual CI. Okay, so in other words, if you compute the gradient of f, you have to compute the gradients of the CIs. But having computed the gradients of the CIs, you've got part of the Hessian for free. Okay, and the second part of the Hessian, it's got CI and the Hessian of CI in it. But very often you can get away with just using this term as an approximation to the whole Hessian. And that's exactly what the Gauss-Newton algorithm does. Okay, and okay, so and also there's this Levenberg-Marquardt idea where you toss in a multiple of the identity and so on to restrict the size of the step. So these are all classical techniques for nonlinear least squares, and there was a lot of work of that on these methods in the optimization community. I'd say through about the mid-80s. Okay, and the reason I brought this up was that I was back in 1988. I was in a thesis defense in a statistics department. And the student was using Gauss-Newton, and I said, well, Gauss-Newton is known not to be very fast, at least asymptotically, in the case where these residuals are large at the solution, all right? Because then this term is not a very good approximation to the Hessian. And one of the other people on the committee said, well, if you've got a large residual solution, then the model is wrong, so who cares about slow convergence? Right? So I've always remembered that because it was my first lesson that the statistical context is actually important, right? So here was a statistician telling me that I shouldn't just be blindly solving this problem. I should be asking questions about the context. Okay. All right. Robust linear regression. So this is another source of non-convexity recently. This is where you have a linear model and possibly a regularization term with a parameter lambda. So, of course, there are variants of this problem where both the H, the loss term for the residuals, and the regularizer, either or both of those could be non-convex. And there's been some work done on these things in recent years. For example, this Tukey biweight function for the residual, where it starts out, if you're close to zero residual, it looks like a traditional quadratic least squares loss, but as you get larger residuals, it tends to flatten out. And then when you're talking about the regularizer, these MCP and SCAD regularizers have been proposed that have sort of similar shapes to that. So that's another source of non-convexity. In matrix optimization, in low-rank matrix completion, for instance, you're seeking a matrix X, which is m by n. You suspect that it has low rank. The data that you've got to work with are linear operators on X, on the elements of X. Which are given by the observations yj. And so you solve a least squares problem where you try to find the x that matches the observations as much as possible. So that you can formulate this as a non-convex problem by explicitly parameterizing x as the product of two skinny matrices and just plugging those into the formulation and then just treating that as a non-convex optimizer. Now this is an example of something where there are properties of this function. If you're prepared to make assumptions about the observation operators AJ, and you're prepared maybe to do some sort of appropriate initialization, followed by gradient descent, that there is some hope of finding the global minimum, okay? And traditionally, if we just take a general non-convex problem and treat it as a black box, don't really delve into its properties, then of course there's a possibility that there are useless local minima all over the place. But this is one of many examples where, in machine learning, or one of several examples where, in fact, there is some hope of finding the global minimum if you're a little bit careful about how you design the algorithm. Another property of this formulation is that If you do have a saddle point, if you've got a point with a gradient 0, but there's negative curvature, it has the so-called strict saddle property. In other words, the Hessian is guaranteed to have a negative eigenvalue. And that's very useful in algorithms such as the one that I'll talk about. And then, of course, there's deep neural nets, which we heard all about in Peter's talk, and I don't have to explain what these are, just a composition of a bunch of linear functions. And the game, of course, is to find appropriate parameters for all these transformations so that you get good prediction performance in the end. Okay? And so, you know, the objective that you have to use here is a summation over the training data of an appropriate loss function. This is generally nonlinear and non-convex, and of course stochastic gradient has become the juggernaut. In this context, it's the method of choice. There are many, even in applying stochastic gradient, there are several issues, mainly to do with step size selection and the schedule you use for altering the step size, but also to do with batch size and so on. And these, really on their face, these are engineering issues, right? And I think a lot of the work in implementing and applying deep neural networks is kind of engineering work. But as I mentioned a little bit earlier, they affected generalizability too. So they have important theoretical consequences as well, which I think are only beginning to be understood. And are the local minima global? Of course not, but you can tell these slides are updated in real time because Peter, of course, gave some special case where you could say something about local minima. Okay, a couple of slides. You notice I'm tossing in a lot of random stuff here, but I worked on an application over the last couple of years of using neural networks to detect outages on a power grid from so-called phasor measurement unit measurements that are taken from different points on the grid. So when a line goes out on a power grid, it causes, of course, because of the laws of physics, the power gets routed in a different way on the grid, and it causes these sensors to, of course, give out different readings. And so we're trying to infer from these readings what the outages were. And it's not a clean problem because the physics of the grid depends very much on the amount of power that's being pumped into the grid and the amount of demand at the grid at any given time. And so it's not a nice clean problem. The signature of each outage is broadly the same, but it does depend on, you know, what's been happening in the grid. So it becomes sort of a multi-class classification problem. Okay, and the first attempt that we did at this, of course, just did straight multi-class logistic regression. But the problem with that is that very often the classes are very kind of mixed together. So this is the raw data, the first two of the principal components of the raw data for 5 different classes, and you can see they tend to sort of blend into each other. And we tried a bunch of pairs of principal components, and it was very hard to separate several of these classes, although the green and the purple seem reasonably well separated there. But when we ran this through just a very shallow neural network, just with a single hidden layer, we found that the separation became better, okay, and we trained it appropriately and so on. Now it's clear that you can separate out at least 4 of the classes pretty well. These two look like they're overlaid, but if we take a couple of different components, it turns out they're separated too. So this sort of illustrates the effect that even a shallow neural network has in transforming the raw data into a form that makes ultimately the classification task easier. Okay, so the second part of my talk is about these methods we've been working on for smooth, non-convex optimization with some sort of guaranteed complexity. So the game here is I'm simply trying to minimize a multivariate function, f of x, and I'm trying to find a point that's close to a second-order necessary point. That is, it's got a 0 gradient and a positive semi-definite Hessian, okay? I'm going to assume throughout that the function is bounded below by some known lower bound. So if you're working with a loss, often you can just take that lower bound to be 0. And also I'm assuming a lot of smoothness here. So first of all, the gradient is Lipschitz continuous, and the Hessian is also Lipschitz continuous over this domain of interest. Okay, it's defined by the initial point. All right, so given those properties, you can immediately write down at any point x, you can write down a upper bounds on the function f. You can get a quadratic upper bound using the Lipschitz constant for the gradient. You can get a cubic upper bound using the Lipschitz constant for the Hessian. And they turn out to be very useful in designing and analyzing the algorithms. Okay, so we're going to look for an approximate second order necessary point. So this is one where the gradient falls below a certain threshold and where the Hessian has all its eigenvalues bigger than some minus epsilon, okay? Where these are both small positive tolerances. And I'm looking for complexities in terms of these epsilon values for the number of iterations or the number of operations, fundamental operations you need to achieve, to find a point like that, okay? So what do I define the fundamental operations to be for purposes of this talk? I'm going to say that the basic operation is either a gradient evaluation or a Hessian vector product. That is a product of the Hessian with an arbitrary vector. I'm not going to be assuming that we're required to compute the Hessian explicitly. Okay, all I require is that if you give me a vector, I have to be able to tell you what the product of the Hessian with that vector is. And of course, there are ways of doing that. You can use computational differentiation, which will give you an exact Hessian vector product, or you could do a finite difference approximation to get an approximation to it. Okay? And these things cost roughly the same. So I think it's justifiable to consider them jointly as the fundamental operation. Okay, so of course this is a canonical problem in optimization that's been floating around forever in the optimization literature, and there are a bunch of classical algorithms for solving these. Newton conjugate gradient, which is what I'm going to talk about, quasi-Newton methods and limited memory quasi-Newton methods, nonlinear conjugate gradient, and so on. And the traditional analysis said that, okay, accumulation points are stationary points, and that if you get close enough to a second order sufficient point, that's one where the Hessian is positive definite, you can get maybe fast local convergence if you're using the right algorithm, okay? And there's a summary of these in this textbook. Okay, so since 2006, there was this paper by Nesterov and Polyak that kind of spurred a lot of interest in getting complexity guarantees. And so since then, there's been a bunch of work in the optimization literature on using cubic regularization, that is a model based on that cubic upper bound that I mentioned earlier, or going back to look at trust region methods, which are guaranteed to have accumulation points that are second order necessary points. So going back to those methods and tweaking them in a way that can guarantee some sort of complexity bound as well as some asymptotic guarantee. And so the first paper in that strain that I know of is this Nesterov-Polyak paper, but there are these other recent works as well, mostly in the optimization literature. But this problem's also spurred a lot of interest in the machine learning community, and of course machine learning people are doing optimization as well. And so they've come up with a bunch of methods that sort of amalgams of convexification techniques, accelerated gradient, trust region, gradient descent with some injection of noise, judiciously injecting noise to bump them away from saddle points and so on. And so just in the last 3 years or so, there's been a bunch of methods along those lines. Okay. So I want to start off, I just want to spend 2 slides explaining how you can get a very simple method that achieves pretty good complexity, pretty good global complexity, all right? So again, this is the setting where I've got a Lipschitz continuous gradient and a Lipschitz continuous Hessian. So I'm going to show you a method on 2 slides which can achieve an approximate second order necessary point, satisfying those tolerances that I mentioned earlier, in order of this many iterations, epsilon g to the -2, epsilon h to the -3. And that's not actually that far from the best bounds you can get. Okay, so here's the method. It takes 2 kinds of steps. First of all, if the gradient is above this threshold, epsilon g, it takes a classic short step, steepest descent step, with a step length of 1 over the Lipschitz constant for the gradient. And that's guaranteed to give an improvement in f, okay? Secondly, if the gradient is below this threshold, then it looks at the Hessian, and if the Hessian doesn't satisfy the required condition, that all the eigenvalues are above minus epsilon h, it finds a direction dk that captures the most negative eigenvalue, lambda min, that has unit step, unit distance, and that's a descent direction. It goes downhill with respect to the gradient. Of course, you're free to flip the sign of dk and still satisfy this property here. So you can choose the sign to make sure that it goes negative with respect to the gradient. So if you have this kind of step, then I'm going to take a step length of this long, 2 times the absolute value of lambda k min divided by the Lipschitz constant for the Hessian. Okay? So this is 2 kinds of steps, well-defined step lengths. Okay? So here's the analysis. You can do it all on one slide. First of all, if you take the first kind of step, using that quadratic upper bound, you can show that f decreases by this much, okay? If you take the second kind of step, then you just use the cubic upper bound. You just go at one more term in the Taylor series, plug in the value of alpha k I had from the previous slide, and simplify a little bit, and you get this much decrease related to epsilon h cubed. Okay, so regardless of which kind of step you take, you can actually quantify the amount of decrease in terms of those tolerances. And then just taking the difference between f of x0 and f low, which is the lower bound, you can divide by the amount of progress that you're making at every step, and that gives you a complexity. So you can see you essentially just invert these two, or take the reciprocals, and you end up with, well, this is the guaranteed amount of decrease at every iteration. If you divide the initial error in f by those amounts, you end up with this complexity. So you see the epsilon g to the minus 2 and epsilon h to the minus 3 popping out. So to get to optimality, the lowest complexity methods essentially reduce or improve this dependence to epsilon g to the minus 3 over 2. But the price you pay is you need a much more elaborate algorithm, and that's what I'm going to be talking about. Yeah?
Are there low bounds into these epsilon g and epsilon h?
Yeah, I haven't thought much about lower bounds, but there may be. Yeah, I don't know. I guess you could cook up a function where it takes this long.
So who is the first one that analyzed this algorithm?
Well, I came up with this example. I think I've seen it somewhere else as well. But you mean this particular algorithm?
Right.
Well, I don't claim to have invented it, but I came up with it when I was writing up some slides on this a couple of years ago. But it's been floating around in the folklore before, I'm sure. Yeah.
How do you find DK?
Sorry?
Are you going to say how you find DK?
DK. Oh yeah, right. Yeah, I'll say something about that. Yeah, that's expensive. Yeah. Any other questions?
There are some things that are sufficiently obvious.
All right. Okay. So
that they get reinvented.
okay, you have to work really hard to get from this to this, as we'll see. Okay. So all right. So the cost of this is the iteration complexity. Now, what about fundamental operation complexity? Well, if you're taking this kind of step, clearly you just need a gradient. So that's easy. That's one operation. But if you're taking this kind of step, you need that dk corresponding to the most negative eigenvalue. How do you find that? Well, it turns out that the tool you can use here is a randomized Lanchos type method. And you can show that if you apply Lanchos, I'll say a little bit more about Lanchos in future slides, you can show that to high probability using order epsilon h to the minus 1/2 iterations, that is iterations of Lanchos, each of which is a Hessian vector product. You can find a good enough approximation to the most negative eigenvalue, okay? And I'll explain that a little bit more as we go. So if you then take this and multiply the epsilon h to the minus 3 by this, you get an operation complexity which has now got a epsilon h to the minus 7 over 2 in it, okay? Which is a little bit, so you pay a price for using the second kind of step. And I'll explain this a little bit more when I talk about the method that we worked on. All right, so a comment here is that some of the low complexity methods that were proposed in the last few years are sort of not very appealing in practice. They're sort of these Frankenstein monsters of accelerated gradient and convexification and a bunch of other techniques. I wanted to go back and take one of the classic methods, and Newton CG is one of the classic methods. It's where you take the Newton equations and solve them using conjugate gradient, and try to see if we could retool that in a way that could give us complexity guarantees. And I wanted to use only gradient evaluations in Hessian vector products, and I wanted to match the worst case complexity results. So we have a paper that's about a year old now where our first attempt at this, and this is work with my postdoc Clement Lullier and student Mike O'Neill. So our first attempt at this was a line search method, and it took 4 kinds of steps: steepest descent, a negative curvature step. These are the 2 kinds of steps that I've already talked about for that basic method. But it also used Newton steps and damp Newton steps, where the damping had this epsilon h parameter in it. And so it had 4 different ways of computing steps, but for each kind of step we had the same sort of backtracking line search. Okay, and we could show that you achieve pretty much optimal complexity rate. If you set the epsilon h to be the square root of the epsilon g, then you can show that the overall complexity is epsilon to the minus 7 over 4. Okay, how did I go from 7 over 2 to 7 over 4? Well, I just defined epsilon h to be the square root of that, so that turned that into a minus 7 over 4. Okay, why do I do that? Basically, I just did it so that those two terms that appear in the complexity match each other. Okay, there's not a particularly good reason to make this choice otherwise. Okay. Okay, so a more recent work that we put on arXiv a couple of months ago was this a simpler kind of stripped down procedure, and it's different in a couple of ways. First, it only takes two kinds of steps. One is an approximate damp Newton step, similar to what we had in the previous algorithm, and the other one's an approximate negative curvature step. Okay, and again, it does the backtracking line search along each one. So there's two new features. One is that we don't necessarily need to use randomized Lanchos anymore. It turns out we can use a randomized version of CG to find negative curvature directions, okay, which I'll explain a little bit about in a moment. And the second one is that when we're using conjugate gradient to find this approximate Newton step, we have a way of making sure that it doesn't take too many iterations. So we can force it to stop after this many iterations. Or we can engineer things so that it stops after that many iterations. So in this method, we really are just doing Newton, and we can just do Newton and conjugate gradient, okay? We don't necessarily need any other tools anymore. And we end up with the same sort of complexity expression, order tilde, that means I'm ignoring log epsilon factors here, epsilon is minus 7 over 4. You can actually prove something a little bit more. You can get to stationarity, you can get to approximate stationarity guaranteed in this many iterations. You don't need, there isn't this small probability of failure. The probability of failure, by the way, comes from the fact that if you're using randomized methods to find negative curvature, they may fail. If you're really unlucky, they may fail, because you may not start with a component in the negative curvature direction. But that doesn't matter if you're just looking for a first order point. Okay, so there are three basic components in this algorithm. The first one is a modified CG procedure. Now, conjugate gradient, of course, is a procedure that only works when the matrix is positive definite. So here we're applying it to a matrix that may not be positive definite. So what does it do in that case? Okay, that's what we had to work with. The second component is a minimum eigenvalue oracle. So this is something where, this is an oracle where I give it a matrix and I say, find me a direction of curvature less than minus 1/2 epsilon. That is a direction where the curvature of the matrix in that direction is less than this, or give me a certificate that all the eigenvalues are bigger than minus epsilon. Okay, that's the second component. And then you tie these two components together into this outer loop, which I'll mention at the end. Okay. All right, so here's the modified version of conjugate gradient. So the modifications are in red. The guts of it is just traditional conjugate gradient, which I don't need to explain because it's probably familiar to anyone who's taken a numerical analysis course. But it's a workhorse method for solving h bar times y equals g in this case, okay? But the modifications come in these, basically in the termination test. So at the start, we define a bunch of tolerances here, and but everything is the same until we have to perform a bunch of somewhat non-standard termination tests. And we also crash out here. Notice that if the initial direction is already a direction where the curvature is small, along this h bar direction, then we crash out, okay? And we also crash out if we detect small curvature directions later on as well. Okay, so what are these non-standard termination tests? Well, there are 4 of them. The first one is totally standard. The first one is just if the residual drops below a small multiple of the original residual. We conclude that we found an accurate solution to this damp Newton system, okay? 2 of the other tests are if we come across a direction where the curvature of h bar is small. Now notice h bar here is the damped version of the Hessian. I took the Hessian and I added on 2 epsilon. So if the curvature in h bar is small, that means that the curvature in the original h is below minus epsilon, okay? And so in that case, I figure I found a direction of negative curvature in the original Hessian, so let's use that as the step, okay? Negative curvature step. The 4th one is the weird one. The 4th one is the one that says if the residual, after j iterations of conjugate gradient, is not decreasing rapidly enough, then what that means is that h bar, that's a symptom of h bar having its smallest eigenvalue below epsilon, okay? Because the decrease rate you can show using the convergence theory of conjugate gradient, that if the condition number is a certain value of the matrix that you're working with, you expect to see a certain decrease rate in the residual. If you're not seeing that, that's a symptom that the original matrix does not have the conditioning that you thought it did. In other words, its smallest eigenvalue must be below epsilon. And if the smallest eigenvalue of h bar is below epsilon, then the smallest eigenvalue of h is below minus epsilon because of the shift property, okay? So there are these four termination conditions, and these are the, great, and these are the respects in which it's different from conjugate gradient. If the fourth property happens, if it turns out that you're not decreasing the residuals fast enough, you can use this technique that I think originally is due to Sebastian, where you can infer from that you can get a negative curvature direction by going back and looking at the previous conjugate gradient iterations. And it turns out the difference between the latest conjugate gradient iterate and one of the previous ones, at least one of the previous ones, gives you this low curvature or negative curvature direction. Now we had to adapt this analysis, the argument that Bubeck made, and there's another one in a similar argument, I believe, in this paper of Carmen and Ducci and so on. We had to adapt that for conjugate gradient, and it's a very, very technical argument, but it turns out it gives you a nice way of extracting negative curvature directions. Okay, so what we can show is that modified CG procedure needs this many iterations. It's again order epsilon to the minus 1/2. And that's a similar sort of rate that you see if you were to apply just a Nesterov accelerated gradient procedure to the same quadratic problem. But conjugate gradient, I think, has better properties. I mean, there's a very rich convergence theory associated with conjugate gradient. Its asymptotic theory is similar to accelerated gradient, but I would say that in practice it has much more appealing properties. And so it's nice to show that we can use it and we can get the same sorts of complexity results as you can get for accelerated gradient. Okay, so that's the conjugate gradient component of the method. The other component is one that explicitly finds minimum eigenvalues of a given matrix. So I give you a matrix H, and I give you some probability failure delta, and I ask you to come back with a negative curvature direction, okay? Or else a certificate that all the eigenvalues are above a certain level. So as I mentioned earlier, this randomized Lanchos procedure, which appeared in the literature about 25 years ago, shows that you can do that with this amount of with this amount of work, order epsilon to the minus 1/2 iterations. What we did was to show that you didn't need to use Lanchos. You could use conjugate gradient instead, and basically it has the same complexity. So here's the relationship between the two. These two methods, of course, are very closely related, Lanchos and CG. They both work with the same Krylov space. So after t iterations of Lanchos, what you're doing is, from a given random initial vector b, what you're doing is finding the vector in this Krylov subspace, b multiplied by all the powers of h up to power t. You're finding the minimum eigenvalue in that subspace, or the minimum eigenvector in that subspace. Conjugate gradient is doing something a little bit different. It's finding the minimum of this function in that same Krylov space. So it's got this offset, it's got this linear term that's an offset here. So it's not giving the same answer, okay? However, you can show that basically both of them will find the negative curvature direction at the same iteration. If you run Lanchos and conjugate gradient side by side, if after j iterations the Krylov subspace contains a negative curvature direction, they'll both find it at the jth iteration. They'll give a different answer, but they'll both come up with negative curvature directions. Okay, and it's a pretty simple proof. It's about a page of argument. And of course, it's more appealing to use conjugate gradient because you can implement it much more efficiently. You don't need as much storage. So here's the algorithm that ties it all together. It's very, very simple and actually related to that stupid algorithm that I had earlier, that really two-slide algorithm. That is, if your gradient is above a certain threshold, you try to do a damped Newton step, and you come out with either an approximate damped Newton step or a negative curvature direction. If the gradient is below that threshold, you just call a minimum eigenvalue oracle and look explicitly for a negative curvature direction. That's it, okay? And then you just do a backtracking line search along those two, along whatever direction comes out of that. So we got some numerical results, and I've got, what, 3 or 4 minutes left? So we got some numerical results. We tried implementing this on this Tukey byweight function. Ducci had done this, Carmen and Ducci and others, their paper last year, they tested on the same function. We tried our method. We actually didn't use backtracking. We used an extrapolation bracketing type line search method. We also implemented nonlinear conjugate gradient and LBFGS, all with the same line search, and also heavy ball. Now, even though this is a nonlinear function, we tried heavy ball with just some guess of the momentum term. Steepest descent is really slow on this problem. And unlike most numerical results sections, we didn't always win, okay? So we didn't always get the best results. In fact, most of the times we didn't. And it turns out that these four methods found different local minima, and nonlinear CG usually found the best local minima, but not always. And also nonlinear CG, which is the yellow line, tended to converge faster. So this is the gradient norm. So it tended to go faster. We are sort of somewhat similar to LBFGS, and heavy ball is somewhat slower, okay? And gradient descent is really slow. Now, not always. There were some cases where Newton CG does find a better local solution and has similar performance to LBFGS. On 1,000 random runs with randomly generated data, we found that consistently nonlinear CG, which is now the red line, was consistently fastest. LBFGS and our Newton CG algorithm were similar, and heavy ball was somewhat slower. Okay, if you take out heavy ball, you get a similar plot. And here are some very simple results on some very small matrix completion problems, very low dimensional here, but rank 15, using that non-convex parameterization I talked about earlier. And here we implemented Newton CG, nonlinear CG, and an alternating direction method, which optimizes with respect to U and V alternately. All of these have no trouble finding the global solution. There's no noise in this problem, so the global minimum has residual 0, and they all find that easily. And it turns out that this time we're somewhat more competitive. Newton CG and nonlinear CG, if you count up how many function values are needed, Newton CG is actually faster. Nonlinear CG in this case is somewhat slower. If you count up the gradient evaluations or gradient and Hessian vector products, it turns out that Newton CG and nonlinear CG are, again, very similar, okay, in both. And this seems to be universally true. We're running this on much bigger problems now to see what happens. So here are a few questions that deserve more investigation. One is that our proof works for backtracking. It turns out that in practice, it's much better to use some sort of extrapolation bracketing type line search to do a little bit more careful job of the line search. Can we enhance Newton CG to have better properties while keeping the same complexity properties, have better numerical performance, that is? And then I think there are some unresolved issues here surrounding the performance of nonlinear CG and LBFGS. These methods are good, right? They're really pretty good. And there's not that much in the theory to back them up. So there are some classical results in the literature from the 80s and 90s about nonlinear CG that are summarized in this book. But they don't really capture why they behave pretty well in practice. And similarly with LBFGS, the analysis of LBFGS basically has the flavor of it's not too much worse than steepest descent. The direction you get from LBFGS is basically pointing in the steepest descent direction. And it doesn't really say much more than that. But in fact, of course, its performance is much better than steepest descent. So why is that? I think these are things we need to understand better. Thank you. I'm done.
More questions from the audience?
Done, yeah.
Your nonlinear CG, your non-convex CG, how is it different from Stuyhaug? And it seems to have the same flavor.
Yeah, a little bit the same flavor. Well, first of all, they didn't have a complexity. In their method, though, they just kept doing CG iterates until they picked up a negative curvature direction, and then they headed for the boundary. So there wasn't a complexity associated with that. And the danger with that is you could do sort of a huge number of CG. You could do up to n CG iterations before you found that negative curvature direction. And we show that doesn't happen if you use this damping. You can actually reliably identify the negative curvature direction in a guaranteed amount of work. But it is related to that for sure. Yeah, and
If you modify the H to epsilon and then apply, Stuyhaug, would it work?
It might well work. I mean, we tried to stay as close as possible to the original simple Newton CG, of which that's the canonical form. So yeah, the hope is that it would basically, be the same thing.
Okay, thanks, Steve.
Sure, thank you.